Hello, welcome to this video. In this video we will explain one of the steps of the energy balance, the estimation of energy flows. As you might remember from the energy balance, it's built up from different energy flows: transmission, ventilation, solar gains and internal gains. In this video we will discuss the energy flow transmission. Transmission losses or gains are those amounts of heat which flow through the building envelope from the warm side to the cold side of the envelope. Transmission losses have nothing to do with air flowing in and out of the building. Transmission losses arise from the simple fact that there is a temperature difference between inside and outside. There will always be a heat flow from the warm side to the cold side. The amount of transmission losses or gains is dependent on the building characteristics, like wall construction and insulation, and of course on the indoor and outdoor temperature and also the wind. In this video we will use two extreme weather conditions for the examples: very cold in winter and very warm in summer. Let's first consider the winter conditions, with an outside temperature of -5 degrees Celsius. As you can see, the indoor temperature is higher than the outside temperature, which means that there will be transmission losses via the roof, windows, walls and ground. In summer, when it's hot, the opposite is true. Heat will come in. How much heat you gain or lose due to transmission is not only dependent on the temperature difference between inside and outside, but also on how well your building envelope is insulated. The amount of transmission losses through walls, roofs, floors and windows can be estimated quite easily. Let's take a wall as an example. The transmission heat flows through a wall is the product of the heat transfer coefficient, U, multiplied by the surface area of the wall, A, multiplied by the temperature difference between outdoor and indoor. The heat transfer coefficient, the U value, is the reverse of the overall heat resistance, the RC. Note, because we make use of the difference in temperature, we are allowed to use the unit degrees Celsius for the temperature. This won't change the result, but scientifically you should use Kelvin as a unit for temperature. Let's look in more detail at the thermal resistance. The heat resistance depends on the thickness of the wall and its thermal conductivity. The thermal conductivity is a material characteristic. Polystyrene, for example, which is often used as an insulation material, has a very low conductivity, while steel has a very high conductivity. This means that based on the thickness and the materials used in a wall, you can determine how much heat losses or gains you will have through the transmission. This term, thickness divided by lambda, is the resistance of the wall itself. It's about conduction through the wall. This is also what is indicated on an insulation plate, for instance. Let's look at this example. Here you see a label of a polystyrene insulation board. It shows us the thermal conductivity and the thickness. This gives us enough information to calculate the thermal conductivity of this specific insulation board. Take a moment and try it by yourself. Ready? We divide the thickness by the thermal conductivity and find a value of 5.54 square meter Kelvin per watt. This is also indicated on the label, as you can see here. In addition to the resistance of the material, the overall heat resistance accounts for two other terms, one divided by alpha O and one divided by alpha I. These represent the combined convective and radiative heat transfer coefficient from the wall surface to the air and other surrounding surfaces. For outside alpha O and for inside alpha I. You could calculate those convective and radiative heat transfer values depending on the wind, but you can also use an average. For the indoor convective and radiative heat transfer coefficient, alpha I, you can assume a value around 7.5, while outdoors you should assume a value around 25. This corresponds with an average wind velocity of 5 meters per second and a horizontal flow direction. For simple calculations, you can use these standards all over the year. But please note that the resistance is always expressed in square meter Kelvin per watt, while the heat transfer coefficient is in watt per square meter Kelvin. And of course, in reality, walls are not that simple. Walls are not conducted only out of polystyrene. Walls often consist of at least 3 layers in a wall. For example, gypsum, insulation and brick. If you want to calculate the U value of such a wall, you can use this formula, which is all basic thermodynamics. In this U value, we are accounting for the resistance of each of the layers. The resistance are in series, and the total resistance is the sum of all of them. We have looked together at the example of a wall. The transmission losses of roofs and the ground floor can be calculated the same way, although one has to realize that the ground floor is adjacent to the ground instead of the outside air. So in the formula, you should take the ground temperature instead of the air temperature into account. And for windows, it's also exactly the same. When there is a temperature difference across the window, there will be transmission heat flows, and these have nothing to do with opening the window or solar radiation. Be aware of a small practical difference between walls and windows. If you buy a window, what is indicated on it is the overall U, while for wall materials the R value is mentioned on the product. Note: so now you know how to calculate transmission losses through surface areas like walls, roofs, floors and windows. But there are also transmission losses occurring at the junction in a building. For example, the junction of walls and windows, window frames, or the junction between walls and balconies. If those junctions are not properly designed, heat losses will occur. We call them thermal bridges. They do not only cause extra heat losses, but they also cause damage to the construction or interior because of condensation. Heat losses through thermal bridges can be calculated based on the equations in this slide. The linear thermal transmittance of the thermal bridge multiplied by the length of the thermal bridge multiplied by the temperature difference between indoor and outdoor. The proportion of heat loss due to thermal bridging is typically around 10 to 15%. This can increase to around 30% in very well insulated buildings with poorly designed or realized construction details. But although thermal bridges are an important factor, in this course we mainly focus on transmission through surface areas and will often neglect the heat losses through thermal bridges. A few examples to give you an idea of the thermal resistance of different types of constructions. The RC value of single glazing is very low, while the insulation of a cavity wall with 100 mm insulation is a lot higher. A cavity wall is a wall with a space between 2 layers of the wall. This space can be filled with insulation. Very high insulated glass has an RC of 0.38, which for glazing is very good, but you can see that compared to an insulated cavity wall, it is still very low. In this table, the example with the highest RC value is the passive house. A passive house wall is a house that is insulated in such a way that you almost don't need an active heating system. The heat that you're producing and your appliances are producing is enough to heat the building to a required temperature. You will see in one of the exercises that this might not always be the optimal solution. So how can you insulate a facade and reduce the transmission losses? In new builds, the facade is often insulated from the outside, because this is the most robust way to prevent potential moisture problems, though we won't go into detail on this in this course. In existing buildings, it is not always possible to insulate from the outside. Therefore, the facades are often insulated from the inside. This has the disadvantage that it reduces the indoor floor area, and that you have to be very careful to prevent potential moisture problems. Another frequently used option for re-insulating an existing wall is to fill the cavity with insulation material. Of course, if there is a cavity. Also with this method, you should be really careful to prevent potential moisture problems. And another disadvantage is that the amount of insulation is limited to the width of the cavity. In the same way, roofs can be insulated from the inside and from the outside. Depending on your building, the ground floor can be insulated via the crawling space. If there is no crawling space, the floor can be insulated by adding insulation on top of the existing floor or between the construction. There are also different types of glazing available: single glazing, double glazing, and triple glazing. The cavity of a double glazing and triple glazing can be filled with different types of gases to increase the insulation rate. For example, air, argon, or krypton. There are many different types of insulation materials available, like for example glass wool, rock wool, or wood fiber plates, all with their pros and cons. Increasingly important for the choice of insulation material is its environmental impact. Some materials have a higher environmental impact than others. This should be taken into account when choosing the insulation material. In this video, we explained the heat losses and/or gains through transmission in a building. You are now able to estimate this for a simple steady-state situation. And we showed you how you can reduce heat losses and gains through transmission.